Hey guys, this is Mr. Sell. This lesson is on representations of a linear pattern. So we're looking at linearity on this part, and how can we tell if something is linear? And specifically we're going to be looking at this for graphs and tables. So in a graph, the only thing we need in a graph for it to be linear is a straight line. That's it. Well, what about in a table? Came out poorly. There we go. A table. So a different way to say that would be that it has to have a constant rate of change. So the rate of change cannot change. The first pattern that we did on that last assignment there. So you studied this pattern in the previous lesson. Use your work from previous lessons to answer the questions that follow. Part A. How many new blocks are added to the pattern from one stage to the next? So if we're adding 2 blocks every stage, we should be able to complete this table. I will give you guys 1 minute to work on that with your neighbor though. Alright, from stage 1 we can see that we're going to start with 3 blocks. And from there we're just adding 2 blocks every stage, so whether you count them for stage 2 and 3 wouldn't matter. I would take 3 blocks and add 2 to get 5 blocks for stage 2. Next stage, 2 more blocks, 7. Next stage, 2 more blocks, 9, and then 11. Very good. So this would complete the table for this one. Alright, part C, show where you see the rate of change in your table. Alright, to see the rate of change, let's focus on the table here. So the rate of change, which is, and I guess we'll write this down too. The rate of change will always compare 2 different things. In this case, we're comparing stages with blocks. And we know that it's an addition of 2 blocks for every 1 stage. And yes, that is being shown in a fraction right there. So where does it show that it is changing by 2 blocks every 1 stage? Between every 1 stage. So for example, that's an addition of 1 stage. But also the blocks then would add 2 blocks between those. So 3 plus 2 blocks would be 5 blocks. As it turns out, this pattern is going to repeat always. So it's going to be 2 blocks every 1 stage, no matter where we look at the table. So let's look at this next one, right? So from 5 to 7, we're going to add 2 blocks, which means we would have to add 1 stage. And again, this shows that it repeats. The nice thing about this is not only is this the rate of change, but it's a constant rate of change, which we'll have to identify here in a moment. Alright, now that we have that, and we know the rate of change is 2 blocks every 1 stage, take 1 minute with your neighbor and complete the graph. Alright, so this is the graph that we should have, or something like it. Don't forget to number the axes and label them as well. So the x-axis we know is the stage number, because in the table it was on the left, and then the y-axis has to be the number of blocks because that's on the right side of the table, and it's always in alphabetical order. So it is always x and then the y values on those, okay? Now another question would be, would we connect the lines? Then it depends on how you define this problem, but some of you may not, or may choose to not connect the points, because you may say, well, how do you get to half a block? And I don't really know how to answer that question. So if you did not connect the points, that would be fine on this one. The last part on this one says, where do you see the rate of change on the graph? So we've already identified where we would see it on the table, but on the graph, this would be between the points. Here's what I mean by that. So let's look at these 2 points, and they've kind of identified it already for us. So if I go up 2, well, up 2 is, and that's what the y-axis represents, is number of blocks. So that's up 2 blocks. And then it goes to the right. So it goes to the right 1, and the x values are represented by stages on this one. So it's plus 1 stage. So that is where you would see the rate of change in a graph. Now again, this is a constant rate of change because it's always going to be 2 blocks for 1 stage. Alright, the simplified form of the equation seems seems like we had that one already, right? The number of blocks equals 2 times the number of stage, the stage number, and then we added 1 to that, right? So that would be our simplified equation. In the simplified equation, we've already identified in that last lesson that the plus 1, this is where we get stage 0. So if I put stage 0 in on the equation, then I would get 1 block. And it's also shown where the x value is 0 and on the line, right? That's where you'd get 1 block, okay? These two are important to identify not only in the equation but in the graph, and we'll of course look at the tables later. But there's something else as well. The rate of change on this one was an increase of 2 blocks every 1 stage. Does the rate of change show up in the equation?
Yes.
Yeah, it's 2, right? So this 2 would represent 2 blocks every 1 stage. That's the rate of change right there. The pattern above is a linear pattern. Describe how a linear pattern grows, and describe what the graph of a linear pattern looks like. So in part F, describe how a linear pattern grows, and again we see it in the table. Its rate of change is constant, and then describe what the graph of a linear pattern looks like. Again, we know that it's a straight line. And this one is a straight line, which makes it linear. All right, how many new blocks are added to the pattern from 1 stage to the next on this one? How many were we adding to this one?
A lot. 3.
Now for this particular pattern, we were adding 3 blocks for every 1 stage. Part B, we should be able to complete that table. So take 1 minute with your neighbor and finish that table. From stage 1, we know that just by counting that block, it would be 1 block. And stage 2 has 4 blocks. And stage 3, 2, 4, 6, 7. Now another thing we could do to figure out these values is, we know it's 3 blocks every 1 stage. So from stage 3, which has 7 blocks, we're going up 1 stage. So we need to add 3 more blocks to that, which would make that 10. And then the next one would be 13. All right, show where you see the rate of change in the table. Let's identify what the rate of change is first. All right, the rate of change on this one, and we've already identified it. It's 3 blocks for every 1 stage. All right, so identifying the rate of change in the table, we can see it's between each 1 stage. So I add a stage here. Then I need to add 3 blocks right there. And from 1 to 4 is an addition of 3 blocks. But this rate of change is shown throughout the table as well. For example, between 3 and 4 also. So it's a rate of change. But like we talked about in the beginning of this one, in order for a table to be linear, it has to have a constant rate of change, which this one does. It's showing as you add 3 blocks, you're going to add 1 stage. So on this one, if I added 6 blocks, how many stages would we have to add? 2. All right? But this is where we would see the rate of change in the table. Now create a graph of these data. Where do you see the rate of change on your graph? Take a moment with your neighbor and answer this one as well, or make your graph as 2. All right, so here's the graph. And again, stage number is the x-axis, and number of blocks is the y-axis. Now again, it asks, where do you see this rate of change on the graph? The rate of change is always found between the points. So in other words, again, if I go up 3 blocks, then I go to the right 1 stage. Very good. Now again, we can show that this relationship is shown throughout any 2 of the points. So if I took this and copied it, I can translate this down here and show it's the same exact rate of change between these 2 points and these two and even these two as well. So the rate of change on a graph is always shown between 2 points. Now if we skip points, then we would have to simplify that as a fraction. Alright, what is the equation that gives the number of blocks t for any stage s? We already have this one. The number of blocks, t, would equal 3 times the stage number, but then we would subtract 2 on this one. Where do you see the different pieces of the equation in the geometric model table and graph? Okay, 3, that's the rate of change. That would be 3 blocks for every one stage. And we've already addressed that negative 2 in the equation. It represents the number of blocks from stage 0. Alright, 2f, is this pattern a linear pattern? Use supporting evidence from each of the representations to justify your answer. So the answer to this one is yes. In the table we can see that it has a constant rate of change. And in the graph, if we were to connect those points, it would be a straight line. And that's all we need for linearity.